distributed localization and control of a group of underwater robots using contractor programming. This work has been done with several colleagues as PhD students, Simon Roux, Jérémy Nicolas, Mohamed Saad, and other colleagues, Fabrice Lebars and Benoît Zer. This work has been presented at SWIM 2015 in Prague. I will present the Scout project. The Scout project is a part of the COMET project. We try to show how underwater robots can perform some coordinate tasks with some collaborative behavior. So the company Matrices is involved in this project. Also, you have the DGA and other companies. So the supervisor are given here, and several students of ENSTA Bretagne in Brest are involved in this project. In this project, you have a boat, and the Scout project, you have a boat and two AUVs, so underwater robots. So at the initial configuration, they are like this. So here is the Scout 1 and the Scout 2. At the beginning of the mission, they are moving. Here you have the boat, the main boat, and the two Scouts have to be positioned at a given position with respect to this boat. So when this boat is moving, then the two Scouts should be able to stay at the same reference with respect to the mother boat here. So this mother boat is at the surface, it has the GPS, but the two Scouts here have no GPS. They are able to find their position by a range-only method. I mean, they can only measure distance between the two Scouts or also between the Scout and the mother boat. They should also solve a problem, a localization problem, in a distributed manner. Indeed, they are not able to communicate that much, so we have a distributed computing problem with low rate communication that has to be solved. So at the beginning of the mission, it is like this. Sorry. After they are entering in the water, and after they have to stay at their reference. What about the controller? For the controller, we shall use a vector field method. I mean, the robot is represented here by the gray box. Sorry. So we have decomposed into two parts, the cinematic part here and the dynamic part here. So if you want, you have the propellers as the input of the robot. The dynamic part has some coefficients which are not very well known, such that here you have a 0.1 which will represent a parameter which is not exactly known. This is an approximation of the dynamic model which is not exactly known, but the cinematic part can be considered as perfect. V is the speed, theta is pitch, psi is the heading. For the controller, you have first an inner loop which aims at simplifying the dynamic part. So if you want, this one is the inverse of this part. If the inner loop is good, then we can assume that the speed of the AUV corresponds to the wanted speed. Also the same for the heading and for the pitch heading. Now, once the inner loop has been implemented, we want the robot follow a field, and in this field we can represent as parameters some attractive target and repulsive obstacle. I will now try to illustrate this with a MATLAB program. In this simulation, you have a robot, red, which has to follow a target, black. And here you have a repulsive obstacle. When we add the vector field, the attractive vector field with the repulsive, we obtain the vector field represented here blue. As we can see, the robot tries to follow the target, but will avoid the obstacle. He will do a compromise. You have the high-level controller, which corresponds to the vector field, and the inner loop or the low-level controller, which tries to move the propellers or the wheels in order to allow the robot to follow the arrows or the vector field. For the Scout project we have, this controller works well, so it will be sufficient. The main problem we have is for the robot is to localize, to be able to know where it is in order to apply the vector field controller. Indeed, P, so the position of the robot, P, X, Y, and Z, is not known. So we'll have to build an observer here. Here we'll have an observer which generate approximation, so an approximation, P estimate, of the position of the robot. And the measure we'll have here is not the position, but it will be related to distances. So what about the localization problem? For the Scout project, we'll have range-only measurements. It means that when we have one robot here and another robot here, we measure the distance between the two robots and nothing else. We don't know the direction of arrival of the ultrasonic wave, which tells you the distance. About the resolution, it will be based on interval analysis or contractor programming. The observer should be robust with respect to outliers. It means that when you measure a distance d between the robot A and G, some of these distances may be wrong. Not too much. Maybe we know an upper bound of the number of outliers we can have. But we should be robust. The computation should be distributed. It means that when you have several robots that are able to measure different distances, we do not have a supervisor which knows all the distances and which can compute everything for all. It means that this robot has a computer inside, this robot has also a computer inside, and so on, and they are able to communicate their result. But of course, the rate of communication is very, very low under the water because we use the sound to communicate. So low rate communication. And what we propose here is to use a contractor programming approach. So what about contractors and I will not recall what is contractor programming, but I would like to make a comparison between matrices and contractors. You have several things in common. Uh, so uh, matrices are used to represent linear application. When you have a linear application, so here represented here, for instance, this one, L, you have two inputs, so here A and H. You have the linear application, and you will have two outputs that are here alpha and gamma. I can represent this linear application by a matrix. So here I have 2 because here I have 2. 3 because here I have 3, and so on. And then, as we can see here, I will have the matrix algebra because the set of matrices is a ring and you can compute, solve equations with matrices, and so on. And software like MATLAB take advantage of this matrix algebra. It is exactly what we want to do with contractors. So let me note that when we use the matrices, we have forgotten different things. For instance, when I have this, I don't know what is A, H, alpha, gamma, so I cannot write that the variable are A and H, and the covariable are alpha, gamma. I know in the linear application, I know what are the input, what are the output, but when I have these matrices, I will not have this information. But of course, when we use a matrix, when we use MATLAB, for instance, we have many matrices. The user, the programmer, always knows what are the variables and the covariable of the matrices he deals with. When you have contractors, it is the same. So what is the analog of linear application? It is constraints or equation. For instance, A times B equals Z. You have three variables. The variables are A, B, and Z. When you have a contractor, it is an algorithm which tells as input, let's say, A, B, and Z, and it will return some contracted intervals such that no solution of this equation is removed. But uh, when we have a contractor, we have no idea of the variables it deal with. When I have two contractors, I can make a fusion. For instance, I have the contractor C1, which is associated with this constraint, and C2 with this constraint. When I want to make a fusion, so from these two contractors, I want to build one single contractor C, which encloses the two of them. Now, since the variable B occurs here and here, they share a common variable, and we need to fuse taking this into account. So I can write this as follows. I make the Cartesian product, or if you prefer, a concatenation of these two constraints, this one and this one. And I will add as an information that the second variable of the first constraint of the first contractor, so this one, the second variable, corresponds to the first one. So it's a shunt between the two circuits, if you prefer. Most of the times, since I know when I have a contractor what are the variables it is supposed to contract, of course I will not always write this, and by an abuse of notation for simplicity, I will write this for short. So it is a fusion of these two constraints. So here I have a picture. I have a picture which means that this one corresponds to the first constraint. So let me see in the previous slide. Sorry. A times B equals Z. So this one is A times B equals Z. And this one corresponds to B plus C equal D. Okay, let me check. Oops, sorry. Yes, it is. Okay, but of course, it is not known. I only know that the second variable, B, is here and is also here. That's why I will uh, uh, I will uh, make this circuit here, and at the output I will do the intersection here. And when I will make the fusion of the contractor associated with this constraint and this constraint, so here it's C1 and C2, I will have 5 variables as input, which corresponds to intervals, of course, intervals, and I will have the contracted intervals as an output. Localization with contractors. I will consider first the situation where I have only one robot, the GIF robot, RJ. I will consider an horizon, I mean a window, a time window, from the current time k, and the time window will have a length which takes the past, like this. I represent like this, the past. Or I can represent also like this, in a line. And the size of these windows is h bar. Okay, so I will remember the past up to a time window of length h bar. So the robot satisfies a state equation which is given by, which has the form, this form. Most of the time it is a differential equation, but here for simplicity I will consider that it is a discrete time equation, dynamic equation. So this should be satisfied for h inside the window. So what will be the observer in our case? I will represent it by a contractor, and this contractor will contract the domain for all the variables that are inside this window. I mean for X, for the GIF robot, inside the window. And since I have this equation, the observer, which has the form, I will take the contractor associated with all these equations, this dynamic equation, and I will perform the intersection. So I want to be consistent with all these equations for all h. That's why here I have an intersection for all h. Okay, now in practice, I have some measurements. So I know the environment a little, and this is a landmark, for instance, or and another landmark, or it can be anything I know on the environment. And always for the sheath robot, I will perform some exteroceptive measurements. I mean some measurements which give me information on my state from what I observe in the environment. So this can be done for uh, one T, for instance, for one time here. And what I represent here in magenta will be an information which has been taken at this time, but it can also be have been taken here or for all. So I will have plenty of contractors like this one, plenty of information. All this information will be associated with this equation. Now to make the fusion, I will have to, that's what I will do now. To make the fusion, I will have to do an intersection. So that's why I will each of them, like this one, I will do a fusion with a state equation like this. So it will be for this one, but also for this one. So that's why I will perform for each k for a fusion with the differential equation, and I will intersect all of them. But because of some outliers, I will perform a relaxed intersection. That's why here, to be robust with respect to some outliers, I will allow my contractor to be inconsistent with Q1 of my contractors. And of course, I make the intersection with my differential equation, and the observers that is written here corresponds to what we call the RSO contractor, robust with respect to outliers. So in fact, I have a formula which is not so easy to understand, but which correspond to an algorithm, and which makes me possible to give in a mathematical form the observer I am trying to implement. Once I have expression for the contractors corresponding to the observers, I also need a paver. So the paver will bisect the boxes, and we call the contractor to contract the box and to give an approximation, an outer approximation of the set of all feasible state or all feasible tube. Uh, if I want to have also an inner approximation of the set of all feasible state, I will be able to use exactly the same expression, but instead of contractors, I will have separators. Uh, I will illustrate here on an example. Assume that I have a robot white, which is able to measure a distance with respect to a mark, here black. So at the beginning, the robot, because of some uncertainty, it will be able to know that it is inside this set. So the feasible set, the contractor will remove all the gray, light gray boxes. But if I have also an inner contractor, or if you want this pair of two contractors will be separators, I will be able to have an inner and an outer approximation for the set of feasible set. If this robot is moving, I will be able to have more information thanks to the movement, to the motion of the robot. So here, step 0, step 1, as you can see, the robot has moved, and so on, it moves. And we can see that after, I will be able to have a good localization of the robot. I will still have inner and an outer approximation, but I will have an uncertain zone, and in this zone, which is not thin, I will not be able to say that one point is inside or outside the set of all feasible states. And this is due to the state noise. Okay, now what about the distributed localization? So I can also apply the same principle. I have one robot J and another robot L. These two robots correspond to the scouts. I will be able to measure the distance. The first one, J, will have its own contractor on a given window of length h bar. It will be also the case for the other robot, and they are able at each K to measure the distance between the two robots. So I will have a constraint between the state of the robot L and the one of the robot J. This information I will be able to represent like this. So when I have such an equation involving interval, it means that there exists one variable inside this interval and one variable inside this interval, such that the equation is satisfied. So the range measurements between the two robots can be translated by this equation. So we can assume for simplicity that for each sampling time I am able to measure all distances, but since I am at time k, I am able to measure this distance only. But I remember all the other one inside this window. So now, the observer I would like to propose is first the contractor for the robot number J should satisfy the state equation. This is this contractor. Should be consistent in a time window with all exteroceptive measurements. This is this contractor, and Q1 corresponds to the number of constraints that are allowed not to be satisfied. And also for all measurements between all robots, I should satisfy the fusion between the state equation and these distances. And again, I am allowed to relax some of them, so Q2. So this is the controller I propose. And what about the communication? So this one, this robot, will contract all its domain. Also, it will be the case for this robot. But these two robots are able at time k just to exchange the domain, so the interval associated with the variable, the state variable at time k. So of course, it would be much better if I could exchange all the tube or all interval in the past. But because of the low rate measurements, I will only accept to exchange uh, to communicate the domains for the state variable at time k. And we'll see that it will be sufficient for localization. I would also like to discuss about the singularity. So there is a singularity for our scoot problem. Remember, I have the motherboard on the surface and it has the GPS, and the GPS can be interpreted as an exteroceptive measurement. This one do not see anything, the two scoots do not see anything in the environment, but they are able to measure this distance, and this one. But assume the situation where all robots go straight on. Is it possible by range only information uh, to localize? In fact, it will not be possible because assume that I change this robot by this robot. What will happen? I will measure the same. I will have the same measurements. Also, if I take the true triangle, and if I turn like this by an angle, the same angle, then all measurements will be identical. Which means that if I go straight on, I will not be able to see the difference between this triangle and this triangle. So what will happen in this case? Since I will not be able to localize myself, I will ask one robot to maneuver. So for the simulation, I have taken only 1 second. I will ask at each step to wait for, let's say, 2 seconds. So 2000 milliseconds. And here I ask to have maybe 200 boxes. Okay, so I will start running the program. And we'll see at the beginning, we have the set for all the Scout 1 and the Scout 2 with at the beginning. And this simulation is supposed to last for 1 second. And we see that more and more, the accuracy for the Scout 1 and the Scout 2 becomes more and more accurate. So here it is the motherboard. Here the paving corresponding to the Scout. So the center of the Scout is here in this side, this set. And what about the second one? The second one will be the same. It is the center is inside this set. If I take only uh, 10 boxes instead of 200, then the accuracy will be, of course, lower, but the system will still manage to perform a localization. And the computing time is lower, of course. So now I will take maybe 1000 seconds. I will remove sleep 100. And if k is larger than 500, I will make a zoom on what happened and I will go slowly. So what happened here? I will ask the Scout if the precision become bad, and I will ask one of the Scout to maneuver. So The robots are here. Now I have the zoom, the target, and here the inaccuracy becomes too large, so this scout decides to maneuver. Immediately the accuracy becomes better, and because he went too far, he comes back to his target, and when the motherboard turns, we can see that the two targets are turning also. So these targets are fixed in the frame of the motherboard.